All right, last class we determined some pole frequencies, and we determined 3 for this low frequency response of a MOSFET amplifier. So what we want to do now is we want to take a look at which one is dominant. There's 3 different frequencies. What is the frequency that actually determines the cutoff for the amplifier? So we can look at I just want to do a little bit of recall here. If we recall S, all right. Okay, at a transmission 0, we can say, or let's say a transmission 0 is a value pen's messing up here, is a value of S at which the input does not reach the output. Okay, resulting in an output voltage of 0. Resulting in the output voltage just equal to 0. That's all it is. So we can say CC1, okay, becomes infinite. Impedance at S equals 0. Okay, so it's open circuit. And it introduces a transmission 0. Transmission 0 at S equals 0. Okay, so it blocks DC, which is exactly what it's supposed to do. It's a coupling capacitor. Okay, we can say exactly the same thing about CC2. Say the same thing about CC2. All right, since it's also a coupling capacitor, so the coupling capacitors are easy. Since it is also a coupling capacitor, okay. CS though is a different story. That's the capacitance on the source of the MOSFET. So I'm going to grab a new page here, and we're going to say CS is a different story. All right. Okay, the transmission is 0 for CS. Zero at the value of S that causes ZS, that impedance, to become infinite. When that happens, IS, ID, and V out become 0. Okay, so we can take a little, if you back up a little bit in your notes and in the book, we can kind of clarify this. Earlier we said we get this transmission 0 on the negative real axes of the S-plane. SZ is equal to a 1 over a negative CS RS. So SZ here, that's S. The shorthand the book uses for S0. So we want, I guess we want to take a look at these three capacitors, and we want to look at what's going on with each one of them. So we want to look at our poles here. So I'm going to say this, another new page. Let's say to determine poles, set the input, V signal or V sig, whatever we've been calling it here, is equal to 0. And you're going to end up with three separate circuits. Okay. If you recall back to your introductory electronics course, you talked about reducing sources to 0. Remember, you short a voltage source, you open a current source. So let's take a look at each of these circuits right now. Okay, if we look at CC1 and we short out the source, we've got source resistance still there, okay? The voltage source itself is shorted out though. Let's say CC1 and our gate resistor here. And our time constant, this is T1, or the time constant for the part of the circuit that involves CC1 is equal to CC1, the value of the capacitor, times the source resistance plus RG. Okay, that's for CC1. Okay, let's look at CS now. For CS, our circuit is a little more complicated, but it's this resistance value here is 1 over the transconductance. We've got RS here, and we've got CS in parallel. And this drops to ground up here. Okay, so there's our circuit here. So we can say tau, the time constant for this circuit, is going to be CS times RS in parallel with 1 over the transconductance. Okay, and we've got one more here. We've got to go CC2. I'm going to add another page. For CC2, we've got RD, our drain resistance. We've got CC2, and we've got our load, RL. So tau for capacitor 2 is going to be CC2 times RD plus RL. Okay. The corresponding pole frequency for each is the inverse of the time constant. Corresponding pole frequency, and we'll do an example of this in a minute. Corresponding pole frequency, omega P for each is the inverse of the time constant. Again, referring back to your second circuits course last spring. So we want to talk now a little bit about selecting these values. For selecting values for the coupling and bypass capacitors. And again, we'll go back to an example in a bit here. We can say selecting values for coupling and bypass capacitors. So let's take a look at that. The goal is to select the appropriate values, obviously, for CC1, CS, and CC2. To place the lower 3 dB frequency, that cutoff frequency, FL, at a specified value while minimizing the cap values. So you want to keep the caps small as they add weight and they take up space. And they also heat up. Okay, so the goal is to select appropriate values. For CC1, CS, and CC2. Place the lower 3 dB frequency, FL, at a specified value while minimizing the cap values. So we're getting into a little bit of design stuff right now. Okay, the trick, there's a trick to this too. Let me add another page. Let's say the trick, at least I call it a trick. Since the resistance seen by CS is equal to 1 over the transconductance in parallel with RS, is usually the smallest. Is usually the smallest of the 3 capacitances. I shouldn't say capacitances, but the 3 capacitive or capacitor resistances. Total capacitance is minimized by selecting CS to provide the highest frequency pole. So you want to select that one so it's closest to the passband frequency. Let's just say this, i.e. making CS's pole frequency FP2 is equal to FL. So that's you want to make that your dominant cap, the cap that sets that dominant frequency, the frequency that's closest to the midband or the passband frequency. So, and we want to pick. We can't forget about C1 and C2. Okay, the other two pole frequencies make them five to 10 times lower than the dominant frequency pole. FP2. I hope that makes sense. You got to be careful with this though. You don't want the values for FP1 and FP3 to be too low, because they could require larger values of capacitor 1 CC1 and capacitor 2 CC2 than may be necessary. So let's put a little asterisk here. Let's just say this: be careful. Though, do not want the values for FP1 and FP2 to be too low, because that could require larger values of CC1 and CC2 that may be necessary. It's very windy here. My camera alerts are popping up. Sorry about that. I forgot to turn my network off. So what we'll do now, and we'll do this in class, we'll run through this example in class. What we'll do is we'll do an example. We'll actually put some numbers in, we'll look at the circuit, and we'll run through some calculations. So I'm going to stop this.